So I will be starting at the beginning. As Sean said, and as he's been telling us, folks in the room have come with a variety of backgrounds. They've been here, varying amounts of time, and had varying amounts of exposure to some of the analytics upon which what we're going to talk about sits. So we start at the beginning in almost every one of our, no, in all of our presentations. It's sort of the very basics, and then we build relatively quickly to where we're trying to get. And as Sean was saying, the package that we've been working together on and that we'll be sharing with you is really about, he didn't say it this way, but the title of this workshop says it exactly the way we think about it, learning about and from variation and impacts. The learning about is, how much of it is there and so on and so forth. But that's the stuff that Mike and I and Steve will be talking about the next day and a half or so. The learning from is like what sort of mediators, what sort of moderators. You can learn from variation about the mechanisms of the impacts of interventions and things like that. So really, I think that's a fairly reasonable way to kind of keep track of the whole package, learning about and from variation in impacts. So what I'm going to talk about is detecting and quantifying variation in impacts. And I'm going to be very clear that I'm going to be talking about variation in the effects of program assignment. You have a random assignment or some other assignment. We're going to be talking about random assignment. But the same basic ideas hold for any kind of assignment to program or control group or alternative treatments and so on and so forth. You can assign somebody to a treatment, that does not ensure that they get it. You can assign somebody to a control group, but that doesn't ensure that they don't get the treatment. So there's often a disconnect, and sometimes a large disconnect in randomized trials, for example, between what people are assigned to and what in the way of the treatment being tested or the intervention being tested, and what people actually get. So what we're going to be talking about first is the simpler. None of this is simple, but we're going from simpler to less simple. Okay. What's the effect of assignment to treatment? You randomize to the treatment group or randomize to the control group. You look at the difference between the mean outcome for the treatment group and the mean outcome for the control group. You get some sort of an average outcome impact of assignment to treatment. That doesn't give you what's the impact of actually receiving the treatment or not. Okay, now the impact of assignment to treatment is something called intent to treat. How many people are familiar with the distinction I'm about to make? Okay, I mean, this is helpful for us to get a sense. So we're going to be talking about intent to treat, the intention to treat, the effect of assignment to treatment or not, first. And then tomorrow morning, Steve is going to add a discussion about, well, how do you extend this kind of thinking through an instrumental variables procedure to estimating variation in the effects of actually receiving the treatment or not. And then things become a little more complex, a little more nuanced. So that's where we're going. And then we'll start trying to explain this variation and impacts with Lindsay's and Guanglei's and Sean's work on mediators. All right, so that's where we're going. So I'm going to be talking about ITT only, intent to treat only. All right. So what I'm going to be doing is defining variation in program effects and detecting and quantifying it. And I'm going to be using two empirical examples, not at great length, but one of them is a secondary analysis of 3 large MDRC. How many people are familiar with MDRC? Just so I know. So MDRC, work welfare studies. These are programs that help poor people who don't have jobs get jobs, or who have crummy jobs get better jobs. And these are people on welfare. Okay, and we've been doing that. That was sort of the raison d'etre of MDRC 40 some odd years ago, is really studying employment programs for disadvantaged populations in the United States. So we were able to put together a series of data sets from 3 large MDRC multi-site projects, and we've done a number of things with that over the years. And so I'll be using a little bit of information from that for empirical examples, that set of studies. And also recently, we and others have done some reanalyses of something called the National Head Start Impact Study. How many people are familiar with that? All right, I mean, it's a very rare thing. It's actually it's a randomized, multi-site randomized trial in a nationally representative sample of sites, which is extraordinary. That second part is extraordinarily rare. Okay, we're now doing a lot of randomized trials. I mean, even 15 years ago, there weren't so many randomized trials, and there certainly weren't many randomized trials in education research. Now there are a lot of them. But there are very, very, very few randomized trials in some sort of a random sample or a probability sample of sites. That's one of them. Okay, and what I'm going to be talking about is basically written in this paper by me and Steve and Mike and a colleague, Kristen Porter. And you have access to the paper in the same place where you'll have access to the slide decks and stuff like that. And I assume Nadia, is Nadia here? No, she's not here. So I assume people know. Do people know? I know Nadia sent you out materials. Did you know how to access this paper? So you know where it all is. So that's the paper I'm going to be talking from. All right. So the first part is starting at the beginning. Okay, individual impact variation. And starting with what's the impact for one individual, and then talking about how does impact vary across individuals, and how much can we learn about that or not. That'll be pretty quick, because there's a limit to what you can learn there. How many people are familiar with the potential outcomes framework for causal inference? I mean, I presume anybody who's taken courses here would be. Okay, all right. So we start with the impact for an individual, and we start expressing it in terms of potential outcomes. So this y sub I, that's the outcome for individual I with treatment, either assignment to treatment, and that's what I'm going to be talking about, under assignment to treatment today, and y sub 0 under assignment to control status. Okay, and each individual is posited to have an outcome under the treatment condition, potential outcome under treatment condition, a potential outcome under control condition. And the difference between those two outcomes is the impact of assignment to treatment or intent to treat for that individual. Okay, so that BI, that's the impact for individual I, is equal to the y sub 1 minus the y sub 2 for individual I. And then you can think in terms of, okay, if you have a population of people, and you want to talk about a population of people, what's the expected value of those impacts? What's the mean of those impacts across that population, somehow defined? It's the expected value of y under the treatment condition and the expected value of y under the control condition. Experiments, randomized experiments, they give you an ability to actually produce unbiased estimates of that mean impact by randomizing to treatment and control. The treatment group gives you an unbiased estimate of the expected outcome under assignment to treatment. The control group gives you an unbiased estimate of the mean outcome under assignment to control status for comparable people, for that population of people, for comparable people. So now we want to go beyond that. Sean was saying that's kind of where much of the research has been over the years, and now we're at least able to do it with randomized trials on a regular basis, so it's getting much more rigorous. But now we want to talk about the variation in P. And now let's talk about variation in the impact across individuals. And let's talk about a population distribution of impacts, okay? So the variance, whoops, is this, yeah. So the variance across individuals in a population of the impact is equal by definition to the variance of the difference between the two potential outcomes. Now, so let's talk about what can we learn about that. Okay, so there's a fundamental barrier to being able to what you can learn about impact variation across individuals. And if you go down to this equation here, just re-expressing the definition of impact for an individual, y under the treatment assignment is equal to y under control assignment plus impact from individual I. Fine. Now, if you want to take the variance of y under the treatment condition, it's equal to variance under the control condition plus the variance of the impacts, which is something you'd like to know something about. It's the variance across individuals of the impacts. But it's not going to be directly observable because there's a potential for there to be a covariance between the impact and the counterfactual outcome, the outcome under the control condition. Okay? There's a potential for there to be a non-zero covariance between B and y sub 0. And you don't know what that covariance is. So what an experiment can give you is the impact. Right. So, and that covariance is a potential substantive interest. And we'll talk about, actually, in the assignment for this, have you sort of imagine what kind of covariance would be. So the notion of a covariance is, would you have larger impacts for kids who would have done badly otherwise, less well otherwise? Or would you have larger than average impacts for kids who have done better than average under the control condition? And there are certain kinds of interventions that are meant to be compensatory. They're meant to serve those children or students who are least well off, who would have done least well or less well than average without treatment, and they would have a negative covariance. In other words, if the impact is biggest when the counterfactual outcome is smallest, that's a negative covariance. So a compensatory program, if it were truly compensatory, would have a negative covariance between those two things. And a best and brightest or something that's geared to bringing up the top end of the distribution of performance or achievement or whatever would have a positive covariance between B and Y sub 0. And there are economists like Jim Heckman and others who have, and Greg Duncan in the field of developmental psychology, who have spent a lot of time thinking about, certain programs compensatory, are they the reverse of compensatory, and so on and so forth. So this covariance is not only, it is a troubling statistic, it keeps you from learning certain kind of things, but it also is of great substantive interest. Likewise, the covariance across sites, which we'll be getting to and Steve will be talking about, there could be a covariance across sites. Those sites that have the biggest impacts on average might have the counterfactual outcomes that are either lowest on average or highest on average. So you can tell a cross-site story of compensation or the reverse of compensation, and you can tell a cross-individual story of that. Okay, and those things are of considerable substantive interest. All right. The point I was getting to, though, is that an experiment can give you a valid, internally valid, unbiased estimate of the impact of assignment on the variance of the outcomes. An experiment can give you, estimate the difference. If you have a treatment group, you calculate the variance of outcomes. You have a control group, you calculate the variance of outcomes. You take the difference between the two. That's an unbiased estimate of the impact of assignment to treatment on the variance of outcomes. If it shrinks the variance, if the treatment group has a smaller variance than the control group, okay, it tells you something about shrinking the distribution of outcomes. If it expands the variance of the outcomes, if the treatment group has a larger variance of outcomes across individuals, okay, it tells you that the treatment is somehow expanding the variance. Okay, so you can get that from an experiment. You can get the impact of assignment on the variance of the outcomes. What you can't get straight up from the experiment, treatment and control group difference in variances of outcome, boom. Okay, what you can't get so simply is the variance of the impacts. That's the point I want to make here. Because the difference, all I did was take the, pardon me, all I did was take this equation here and just subtract this from both sides to get this over here, right? And so what you've got is the difference, the impact of assignment on the variance is equal to the variance of the impacts plus that covariance. So just because the variance is larger in the treatment group than it is in the control group doesn't tell you directly how much variance there is in the impact, because what you don't know and you can't observe is the covariance between impacts and counterfactual outcomes. And before I answer your question, Steve, would you please tell me why you can't observe this term here across individuals? Why you can't observe the covariance between B and Y sub 0? That's right. You know one of the two. I mean, you can call them both. I mean, they're really both counterfactual outcomes or potential outcomes. So you know one for each individual. You don't know the other. Okay, so you're always backing into these things at the individual level. So you can't directly look at that covariance. Does that make sense? And that's sort of the fundamental limit in some ways to what you can learn at the individual level without beginning to impose assumptions. All right? And so I want to move from that, but I wanted to start at the individual level. Steve, you want to say something? Oh, that implies the fact that I modified my slides very close to the time that I was coming out here, and I was trying to get it closer, these slides closer to the paper that you're reading. And I think we might have it expressed both ways in the paper. That explains that. All right. That's an occupational hazard. All right. Any other questions before I move on to the main part of what I want to talk about? Okay. So now, I actually want to just illustrate this point. These are some findings from the National Head Start Impact Study that Chris Whelan, who's a developmental psychologist at University of Michigan, and I have done. It's one piece of a paper that we've written. And just to illustrate the couple of points before we move on about individual variation. Okay, one thing that so these are two outcomes, receptive vocabulary and early reading. Okay, we have it for other outcomes too, but I just want to focus on these two. We estimate a mean effect for the full sample, a mean effect for two subgroups of sample members, defined in terms of observable, not unobservable characteristics. This is sort of standard subgroup analysis. For the lowest pretest quartile, we got pretests on all of these kids. Those kids that were in the lowest quartile of pretest, that's one subgroup. That's a baseline characteristic. All the other kids, those above the lowest quartile, that's another subgroup. And we see that the impact for the lowest pretest quartile is 0.16. The impact for other sample members is 0.08. Now, what I'm going to be expressing here and what these are in is in a standardized mean effect size. I presume everybody's familiar with that metric. It's the impact in its original units divided by a standard deviation, usually a control group standard deviation or some standardized standard deviation. So these metrics are in standardized mean difference effect size, so 0.16 and a 0.80. So this is what's the covariance? Just by looking at this information, what do you think the covariance between impacts and counterfactual outcomes is with respect to receptive vocabulary? Positive or negative, and why? Josh?
Negative.
And why?
Because the lowest quartile is doing better, so coming from a lower part of the distribution is correlated with more.
Right. And then you look down here, and what we're reporting here is the variance of outcomes for the treatment group and the variance of outcomes for the control group in a different metric, in their original units, in the original test score here. And what do you see here? Somebody else. What do you see here? Yes? Right, treatment is shrinking the variance, okay? Then that's the negative covariance at work. That's what Josh was talking about. Now, those kids at the bottom are being pulled up more than those kids at the middle at the top. So that's shrinking the variance. So you see that compensatory effect, pattern of effects, pattern of impacts, both through this subgroup analysis and through this analysis of the variances for the treatment control group. Do you see it? It sort of ties together the couple of points I was trying to make. Does that make sense? And then for this subgroup, for this outcome, though, you don't see much of a compensatory pattern at all, and you don't see much of a difference in the variances. Now, it doesn't work out that clean all the time. I chose my examples carefully, but you get the idea, right? So that makes sense. All right. You know the covariance has to be negative. When the variance increases, you don't necessarily know that the covariance has to be positive. Why? And then I will move on. Because if there was zero covariance, in other words, if on average, every level of y sub 0 had the same impact, if the covariance is 0, this term falls out. There's still a positive difference between the variance in the treatment group, of variance of outcomes in treatment group and variance of outcomes in control group. You see that? Because you got the impact in the treatment group, which is varying across individuals in the treatment group, and you have another source of variation in individual outcomes in the treatment group that doesn't exist in the control group. So if you see the treatment group with a bigger variance than the control group, it doesn't necessarily mean a positive covariance. But Sean's point, if you see the treatment group with a smaller variance than a control group, it must mean that there's a negative covariance. So you're sort of asymmetric on what you can learn here at the individual level about the covariance. You can learn that it's negative when it's negative. If you have enough precision, you can't learn that it's positive when it's positive. So that's just a limitation. So now we're going to switch from individuals to sites, where you can learn somewhat more. And we're going to start with a theoretical model that is talking about variation in impacts and counterfactuals across sites. Variation, you take one site. You've got a mean counterfactual outcome for that site in a population for that site. You've got a mean impact for that site in a population for that site. And the difference between the two, well, no. So you have those two things. And they vary across sites. And this is a theoretical model about how they vary across sites. Now, this model says that the outcome for individual I from site J is equal to A sub J, which is an intercept term for site J. It's a site-specific intercept term, plus B sub J, the site-specific mean impact, times T sub ij, T equals 1 if you're assigned to treatment, 0 if you're assigned to control. You're familiar with that notation. And an individual error term around that mean counterfactual outcome and that mean impact for that site. And that level 2 is a 2-level hierarchical model. But it's at level 2, you have the mean counterfactual outcome, the mean control group outcome for the population, varying randomly across the grand mean counterfactual outcome. If you had all the sites, this is what's called a model of a superpopulation of sites. It presumes that whether you took a random sample of sites explicitly from some population of sites, or you had a convenience sample, but that sample is almost undoubtedly representative of some population of sites, whether you can describe it clearly or not, you're almost always interested in generalizing beyond just the sites you're looking at. So this model takes that very seriously, and it frames it in terms of a superpopulation of sites, which has a distribution of counterfactual outcomes where mean for each site, where A sub j varies across the mean of the site means randomly, with A sub j as a random variant, a random error term. For the intercept, the mean impact for each site, B sub j, varies across the mean of the site mean impacts, beta, randomly with the term B sub j. So that's the theoretical model that we're using to sort of frame our discussion of detecting and quantifying cross-site impact variation. And yes?
Since we assume we are taking a random sample from a population of sites, right? So how many sites do we need to collect this?
Okay, the next presentation, we're going to talk for an hour, we're going to have a break. The next presentation is all about that, okay, very explicitly. Okay, so this is what would we do, how would we do it? And this is the model that we're starting from, the theoretical model. Now what we're going to do then is we're going to come up with an estimation model that we're proposing that has certain properties given that theoretical model, and we'll talk about that model and how to use it and how it works and so on and so forth. That's what we're going to do here, okay? And then we'll talk about how to assess the power of that process, that estimation process. Okay, so some goals of cross-site analysis. One, we want to estimate the grand mean. That's the mean of the site mean impacts. Two, we want to estimate the distribution across sites of impacts. Okay, and we're going to do it through 3 summary statistics of that distribution. 1, its mean, its cross-site mean. 2, its cross-site variance or standard deviation. It's usually easier to think of your findings in terms of dollars instead of dollars squared, or test score points instead of test score points squared. So the cross-site standard deviation of program effects, and then the cross-site distribution of program effects. There's going to be a real limit to what we can do there. We have to make some assumptions to roll that in. But we're interested in that. We want to learn more than just the mean. We want to learn about how much variation there is across sites, and then maybe something about the shape of the distribution. But there's going to be some real limits to what we can learn with respect to the shape of the distribution. And then in addition to that, we want to learn goal 4, something about the difference in mean program effects between 2 categories of sites. Now that is the simplest possible site-level moderator analysis, like rural sites versus urban sites. And what's the difference in the mean impact for rural sites and urban sites, okay? And we'll talk a little bit about the power for that too. Okay, so those are the simplest possible parameters you might want to be estimating from a cross-site distribution of intervention effects. All right. And then in addition to that, and Steve always focuses a lot on this, you want to estimate the mean effect for each site, maybe, to the best of your ability. Because you might want to know, where are the really effective sites? Can we identify them? Where are the least effective sites? Can we identify them? Can we go out and study them and see what in the world was different about how they operated, who they served, whatever, so we can learn more about the future? Okay, that's in part Sean's note about, or point about, getting some science into this instead of just simply reporting out findings. All right, so what's the identification strategy? So a multi-site trial where, and I'm going to just use the word site and leave it at that and just talk about each site. When Mike talks, there's going to be a little bit nuance. He's going to talk about blocks within sites. But right now, each site is an entity, and the designs that we're talking about are within each site, you randomize your subjects to treatment control status. And you randomize them separately within site. Okay, so that's a blocked randomized design, blocked by site. And if you have that kind of design, what that is essentially a fleet of randomized trials. and you can learn about each site's likely impact. And then, unlike individuals, so for each site, when you're randomizing treatment and control, you can estimate the mean under the treatment assignment, the mean under control assignment, and the difference between the two. You can actually begin to look directly at the cross-site variance in the impact. Whereas at the individual level, remember we said there's a limit to that because you can only look at one counterfactual outcome. So we can get beyond the individual limitation to impact variation at the site level. And we can look at a cross-site distribution of impacts of a site. All right. So one thing that is really worth noting is, to the extent that there have been multi-site trials, and they've been reported out, but oftentimes when people summarize their results, they take their point estimates and maybe create a histogram of the point estimates and say, here's a histogram of the point estimates of our impacts, and that's telling you about the distribution of impacts. No, not necessarily. That's telling you about the distribution of impact estimates. And this is not a word game. This is actually a huge issue that a lot of people make a mistake. And I'll illustrate some findings. The impact estimates themselves for site 1, for site 2, for site 3, et cetera, et cetera, et cetera, okay, each one of those impact estimates is with error. And the smaller the site, the greater the error in the impact estimate, right? So when you look at a bunch of site-level impact estimates and you say, how much variation is there in those impact estimates? Okay, there are two sources of variation that you're looking directly at. One is the variation in true effects across sites, which is what you're interested in. And the other is the variation in the impact error, the average estimation error for each site. And they're both there. So the variance of the impact estimate is equal to the variance of the impacts, and I'm going to label that tau square sub b, and maybe you'll see a lowercase b occasionally, I'm not sure. But tau square sub b, that's the variation in the true impacts across sites. That's what you're interested in. And Vj, that's the error variance for each site. It's the standard error of the impact estimate for each site squared, error variance, standard error squared. Okay? So when you plot your histogram, the variance of that histogram is going to be this. Okay? Whereas if what you want is a histogram that has a variance that's this, right? So what you can have is your histogram of your site-level impact estimates could be wildly fluctuating. The histogram could be all over the place, all right? And you'd say, my Lord, the impact variation is gigantic across sites. That could be a total illusion, okay, because most of that variation might be driven by the estimation error in each site. And what you can say with confidence is there's a lot of variation in my impact estimates. What you can't say yet with confidence is there's a lot of variation in my impacts across sites. Again, that is far more than a word game. And one parameter that comes into play here as we think about this whole apparatus is something called the reliability of your impact estimates, the reliability of your site-level impact estimates, which, just like the reliability of a measure in psychometrics, is true variance over total variance. So if your reliability is 0.5, that means that this is about the same size as that, and so a lot of the variation, half of the variation you're seeing in your histogram of your impact estimate is just noise. It's not real. It's an illusion. If your reliability is 0.9, and you should live so long as to have that happen, then the variation in your impact estimates is looking pretty much like the variation in your impacts, and you're sort of in the right place. Okay, so that's an important thing just to keep in mind as we go forward. So how do you get this right? So here's just, I made my point. So now we're going to talk about an estimation model. And Steve's going to talk about some alternative models when he talks this afternoon. But it's a model that we've worked with. We've tested it under simulations. The paper that is the basis for this talk examines it from a whole variety of perspectives. We think it's, at this point in time, it's certainly promising. We think it's fairly robust. It has its limitations, but we're reasonably confident it can be a workhorse in this kind of work. It's the following model. It'll look like a theoretical model, but it'll be a little different. theoretical model had random intercepts and random impact coefficients or slopes across sites, right? That was the first model I put up. This is a model, we call it FERC. We didn't call it FERC in the beginning. Fixed intercepts, random coefficients. It has a fixed site-specific intercept for each site, and it has an impact coefficient that varies randomly across sites. And the model at level 1 looks pretty much like the theoretical model, except in level 2 you learned that these things are not modeled as if they randomly varied across sites. They're modeled as if they're fixed for each site, and they're going to be estimated as if they're fixed for each site, whereas the impact coefficient is modeled as if it varies across sites. Now, why do we do that? It turns out that if you actually use a conventional hierarchical linear model, HLM model, with random intercepts and random slopes, okay, and the random what we call T-bar, T is treatment, or the 1 if assigned to treatment, 0 if assigned to control. T-bar is the average value of T for the treatment and control groups, and T-bar J is in site J. Okay, so if T-bar in site J is 0.9, 90% of the sample is randomized to treatment. If it's 0.1 in another site, 10% of the sample is randomized to treatment. If T-bar varies across sites, okay, and it almost inevitably does, even if you plan to have T-bar balanced, but many times the same across sites, but many times you don't even plan for it that way, because some sites, especially if you're doing lottery studies and you're taking the data as given from charter schools, lotteries and stuff like that, you know, oversubscribed sites, T-bar will be low because there'll be lots of control group members because lots of people who applied didn't get in, and less oversubscribed sites, T-bar will be higher because it won't be as oversubscribed, so most of the people who apply will get in. So if you have T-bar varying across sites and you allow the intercept to vary across sites in your estimation model, there could be a correlation between T-bar and the intercept, which means there could be a correlation in your likelihood of getting treatment and something about those sites, something about what happens under the control condition that would bias everything. Okay, so you could have a correlation between T-bar and A sub j, and that would bias everything we're doing. Now, there are a variety of ways of dealing with that potential correlation, but one way that you eliminate that problem altogether is to have fixed intercepts. Now, fixed intercepts is the equivalent of site centering every variable in your model. Okay, if you put an intercept for each site in your model, it's absolutely algebraically equivalent in terms of the point estimate to site centering every variable. What does that mean? It's equivalent to saying y bar sub ij minus y bar j, site centering that variable, and t ij minus t bar j. And this model can be extended if you have baseline covariates to improve precision, which will add in some models some x's at the individual level. They would be site-centered as well. So everything would be site-centered. The minute you put an intercept in, that's what it does. I'm not going to explain how and why, but that's exactly what it does. It site-centers everything. So now the average value of this site-centered T-bar is what? Now, it's what? The average value, well, for any given site, what is it? The site-centered value of T-bar, the average value of the site-centered value of T-bar is what? 0. Because on average, you're at the mean. So the average deviation from the mean is 0. So T-bar is, the site-centered version of T-bar is 0 for every site. There's no way that that can be correlated with anything about the site at all. Okay? So that essentially is the intuitive reason for putting in a fixed intercept. You could actually site-center the data, and if you do site-center the data, you have to account for the loss of degrees of freedom, 1 per site, and some software packages do and some don't. But if you don't want to have to even think about that and just sort of however you're doing this, it's going to work properly, you can put site-specific intercepts in your model. That's why we have the fixed intercept random coefficient model. Okay? In addition to that, we allow the underlying variance at the individual level. I don't have this on here. Let's see if, well, so that's the site centering version of it. We allow the underlying variance here to potentially be different for treatment group members and control group members. Remember, we were talking before about outcome variation at the individual level, okay, and part of the impact of the treatment could change that variance. the treatment group residual variance could be different than the control group residual variance. We specify that in the model. We allow the treatment group residual variance to be different than the control group residual variance. Now, sometimes that matters, sometimes it doesn't matter. And we can do it in SAS, you can do it in HLM, you can do it in other packages. That's a particular part of the model that can be useful, because if those two variances are different from each other, if the treatment group variance is a lot different from the control group variance, and you run a model that's a heteroscedastic model. We call that TC heteroscedasticity, treatment control heteroscedasticity. And you run a model that's homoscedastic, that assumes it's the same, you can get your standard errors wrong, and therefore you can get your cross-site impact variance wrong. And the paper sort of works that out in great detail. Okay, but if you specify separate variances, which is easy to do, that's one problem that you can get around really easy, one potential problem. All right. Now, another aspect of the model that's important is you could specify a separate residual variance, level 1 variance, individual variance for each site, right? I mean, we're working with the original data. We're working with individual data across the sites for this multi-site trial. You could specify a model that site by site estimated a separate variance at the individual level. Or go even further, site by site estimated a separate variance for the treatment group in a site, and another one for the control group in a site, and then 2 more in these sites, and so on. So you could do that. That turns out that if the sites are reasonably small, can be a very bad idea. And it was something that we didn't understand in the beginning when we started down this road. But early on, we found out it could make a really big difference. If you have small site samples, like in the Head Start Impact Study, this actually grows out of the proposal we wrote, which we won ultimately. But to reanalyze the data from the National Head Start Impact Study, we did it site by site. We estimated a residual variance site by site, and we got results that suggested there was a vast amount of impact variation across sites. And it was unbelievably, and I underscore unbelievably, statistically significant. Okay, and that was in our proposal. Long before we ever learned that we won. Yeah. I like to think there were other reasons, but we can all imagine. Perhaps. So anyway, but we learned long before that proposal was even anybody decided on it, said, holy mackerel, we actually did this wrong, because we did it the other way, the way I just described, where we were pooling residual variances across sites, and maybe we'd keep them separate for the treatment group and the control group, but we were pooling them across sites. Got completely different results. We got impact variation across Head Start sites, fine, moderate to relatively large, not gigantic. And we got statistically significant impact variation across sites, but not like beyond imagination. And then we began to figure out what in the world was going on. And the paper, there's an appendix to the paper that tries to describe what's going on. It's a really ironic kind of thing. Random errors causing systematic bias. It's a very ironic kind of situation. We try to explain it in an appendix in the paper. So we would not recommend that you, to get out of, there are other problems with cross-site variation in the variances. There is a problem, a potential problem, a theoretical problem there, and you'll see. We talk about it more in the paper. I'll describe it. If that residual variance is correlated with impacts across sites for some reason, this model can produce erroneous results. It has to be first of all, the variances have to vary a lot across sites. There has to be a lot of heterogeneity in that level 1 variance. And 2, it has to be reasonably highly correlated with impacts across sites in order for there to be a problem. And then there are some fixes for that too. And those are details in the paper. But this is sort of a long-winded way of describing the full model. Okay? It's the basic model we had right here. Fixed intercepts, random coefficients, separate T residual variance and C residual variance, but pooled across sites. Okay, that's the model we're mostly proposing. All right, now. Those are the results from, just to give you a sense of This is single. This is estimating the. Oh, yeah. This is pooling across sites. So we got an estimated impact on. I don't even remember what the outcome was. 6 points, 6 test score points here. We got a cross-site impact variance of 35. This is the model we propose that you use. The statistical significance for that one, because we're only looking at 3-year-olds at the time, was the p-value was 0.296. When we split the sample up and calculated a separate variance for each site, the mean wasn't so terribly different. The estimated grand mean impact wasn't so terribly different. But look at the estimated cross-site impact variation. It's variance, 261 instead of 36. Okay, and the p-value, there are not enough zeros. There's not enough places in here to put all of the zeros. In fact, I thought it was so great. I used scientific notation because it's a rare day. You have a p-value that's, it's 0.1 by 10 to the minus 10. So we literally, in the spirit of if you got it, flaunt it, we put it in the proposal. But that was just dead wrong. All right. But you get the idea. I'm not talking about something that's trivial here. This is potentially an important issue. Now, these are very small sites. The National Head Start Impact Study is 300 sites with an average size of, 11 or 12 total treatment and control. So that's where this happened. But just as sort of a cautionary tale. Okay. So now, what are we going to report? We're going to report the estimated grand mean. We're going to report the standard deviation, the cross-site standard deviation of program effects. We're going to try to say something about the distribution, cross-site distribution of effects, and something about, for each site, the estimated effect, and something about a difference in program effects for 2 categories of sites. Now, so let me just check. Yeah. So here's some results from our work welfare study from applying the model I just described to data for 59 local welfare offices in, about 15 states, and about 60,000 individuals randomized at those 59 offices. So an average, an arithmetic mean number of sample members per site of 1,176, almost 1,200 sample members. So these are big sites. 59 big sites. That's the structure of that particular multi-site trial. And it wasn't a multi-site trial. It was 3 multi-site trials run by MDRC over more than a decade that after the fact, we put those pieces together. And those trials had been run in similar ways with similar measures and so on and so forth. So we were in sort of a once-in-a-lifetime, for me, situation where we had all of this data for this. So the results I'm going to show you, we did a lot more with this. I'm just going to show you the basic findings. The outcome we are talking about here is total earnings in dollars during the first 2 years after random assign. So that's the outcome we're going to talk about. And so what kind of findings did we get? So the estimated cross-site grand mean program effect, beta hat, estimated cross-site grand mean in site means, was about $875. That turns out to be about 18% of the control group level. An 18% increase in earnings over 2 years is not trivial, especially for a disadvantaged population. Okay, these programs, we already knew they were successful. We're coming in years later to take this data and push it in other directions and look at the variation. All right? The estimated standard error of that, and this is a big sample, not surprisingly, was $137. So, the t statistic was about 7 or 8 or something like that. So that's, the p-value was, the confidence interval was 606 to 1100. That's on the mean. Fine. We sort of knew all that. Now, the new stuff, though, is the estimated cross-site standard deviation of program effects, or this tau hat. So, B. All right, the point estimate is $742. Its p-value was well below 0.001, and we have a confidence interval estimate of 525 to 1048. That's the standard deviation, the cross-site standard deviation in impacts. Okay, using this model, and I'm going to show you some histograms in a minute. Yes?
This is the sort of the right way? Did you do it the bad way where you said like what you just showed us before?
Oh, no. By that time, we were out of that business. Okay, we were well out of that business. Although there, it wouldn't have mattered.
You don't think it'd be?
No, it wouldn't have mattered one whit. We did a bunch of simulations that show it wouldn't have mattered one whit. In fact, there are some simulation results in the paper, in an appendix to the paper, that tries to show you when does it start to matter in terms of site sample size. Okay? So it would not have mattered here. Okay, we did a lot of stuff over a long time. Yeah. All right. That's a good question. Now, another little detail is that the cross-site reliability of the impact estimates was still only 0.5 on those big sites. Now, not all those sites were big, so the harmonic mean value of the average site size was about half the arithmetic mean value. But still, those are big sites, and the reliability was 0.5. So there's still noise in those site estimates. There's still noise in those site estimates. About half the variation you would see in the impact estimates across sites would be noise. Okay? And then the variance of the outcomes for the treatment group members, the ratio of that variance to the control group members is 1.09. So the treatment group variance was a bit bigger than the control group variance. And from that, you can't tell whether the covariance was positive or not. Okay? But you can tell that the impact of assignment on the variance was to increase it by about 9% of what it otherwise would have been. Now, some more stuff. These are just some simple histograms to make a couple points of, in this case, the point estimates, call them OLS point estimates, of the impact for each site. Okay, so this is a summary of 59 impact estimates. And you see it goes from, these are in dollar units here, you know, it goes from the mean is right around, no, that's not the mean. That's not big enough. Yeah, that's the zero. That's just the 0 point. It goes, you know, a lot of zeros, some of them non-trivial, a lot of really gigantic ones, and kind of all over the map. Okay, the mean of the the mean of what are called the empirical Bayes estimates of these 59 site impacts, the distribution of those empirical Bayes estimates. This is a histogram of that distribution. Okay, and how many people are familiar with empirical Bayes estimates? All right, so they are what they are, and obviously this distribution looks a lot different than this distribution, which was the point I was making earlier. Even with big sites, imagine the head start. That's a different head start issue. With small head start sites, the difference between the point estimate distribution and the true impact distribution, the inferred true impact distribution, would be just night and day difference. They're totally different stories. In the middle, pardon? With noise, yeah. Right. Small samples, small site samples, lots of noise. VJ is big relative to tau square. Very big. Could be many, many times it. Okay? Now, the paper also talks about the fact, it's a well-known fact, but then it tries to do something about it with a relatively well-known procedure, or a variant of it. If you just plotted the empirical Bayes estimates, it turns out that they will show a variance that's, on average, too small. Empirical Bayes estimates are something called shrinkage estimators. They shrink each site's estimate to the grand mean. In this case, these are unconditional empirical Bayes estimates. And in a sense, they overshrink. And so this variance, if you computed the variance of this distribution, which is a distribution of the empirical Bayes estimates, it would be certainly smaller than that, but it would also be smaller than your estimate of tau square. Tau square is your best estimate coming out of the model of the variation across sites in true impacts. That's your best guess. Okay? The variance of the empirical Bayes estimates would be smaller than that, and it depends how much smaller. That varies as a function of the data structure. Okay? So there is a simple way to adjust for that, and something we call adjusted empirical Bayes, and there's a precedent for it. It goes back 30, 40 years in the literature, and we show how we did it. It's a very simple process in the paper. And this middle, this is like Goldilocks, too much, too little, just right. The middle distribution is a distribution of adjusted empirical Bayes estimates, which is ensured by construction to have the same variance as our estimate of tau square. So these are sort of graphic devices for sort of presenting the results and illustrating the potential illusion here, even in a large site sample. Okay? Question? All right. So now some important diagnostics. These methods, depending on the data structures, these methods they're robust under a lot of conditions, but They can be fragile under certain conditions, and you want to get a sense of how much confidence you should place in your findings. And so these methods have some diagnostics that at least help you get a sense of the uncertainty that's involved in the findings that you're presenting. So one is just simple caterpillar plots, which many of you have probably just done in other situations. And these will be caterpillar plots of either the OLS or the empirical Bayes estimates and something called the likelihood profile graphs. And let me just talk about a little bit about each one of them. This is a caterpillar plot of the empirical Bayes estimates of site-specific welfare to work programs. So there should be 59 of these if we did this right, one for each site. And it's a best guess and then a confidence interval of sorts around it. And the idea here is to plot from smallest to largest point estimate, plot this thing, and visually, and this is from the welfare to work database, 59 large sites. What do you see? And you're interested in how much variation is there across sites in true impacts, and and how much confidence should you have that you've actually detected real variation in impacts? This is part of what you would be thinking about as you're looking at this diagram here. What do you see here? What pattern of impacts do you see? How much confidence about a statement that said, yes, there's variation in impacts across these sites? True impacts, yes. There are probably very few sites that you could tell the difference between any two sites, given the size of these confidence intervals. And that's not quite what we're doing, although ultimately we're going to, one use to which this might be put is to find the sites down here and the sites up there and go look at them, go visit them, figure out why they were so different. You might be able to distinguish between these guys and these guys, but anything relatively close on this distribution, no way. That's right. Steve. But what this tells me, I'm not sure what this should tell you, but what this tells me is that, yeah, there's variation here. There's a pretty substantial variation. You look at that scale, it's non-trivial variation. And there's enough difference here and here in the confidence intervals to my eye to think, yeah, but we detected some real variation. But that's one diagnostic to use. Now, this is the same thing for the Head Start impact study. This is the same a caterpillar plot, same device. For the impact studies, impacts on the letter word identification, that's early reading. Okay, what do you see here? You see, first of all, it's kind of hard to compare slopes. They're in different metrics and everything else. But this is, appears at least, other than this, far more horizontal than what we were looking at before. This looks more vertical. Again, they're on different scales, but relative to the confidence intervals, though, this is more vertical than this. And these are a bunch of tiny sites, and these are 59 large sites. And it begins to get used. I mean, there's a lot of uncertainty to this under any scenario. But we were able to detect with confidence cross-site impact variation. I think that, as I said before, the standard deviation was $742. I'm going to, yeah. So I want to go back to this, and then I think I'll end. All right, Steve, I'm not going to do the profile likelihood. You are going to do it. Yeah, that's what I thought. Okay, that's what I thought. So you look back here and you say, well, what did we learn? How do you report this stuff? How do you report this stuff? Now change hats. You're not doing research anymore. You're at a place like MDRC, or even if you're in a university and you care about affecting how things are done in education. How do you report this stuff out? This is the welfare to work thing. What kind of things would you be interested in reporting, and how would you talk about them? Let's spend the last 5 minutes talking about these results. What would you say? What would you tell a policymaker? What would you tell a federal policymaker, and what would you tell a local school superintendent? Well, this is not school. A local, someone who's running a local welfare to work office. Yeah. What would you tell? So let's start with a federal policymaker. What would you tell? You know, these results actually changed policy. They had not this analysis of those results. That's way after the fact, but the actual initial findings. But what is this? What would you tell a policymaker? A federal policymaker. Yes.
Before I answer that, is there any insight into why there was variation? Can we tell that at all from the data?
Well, not the data I showed you, but I and Carolyn Hill, who was at Georgetown at the time and now is at MDRC full-time, and a guy by the name of Jim Riccio, who was at MDRC, we did a paper about a decade or so ago that really worked through all of that. And if you're interested, I give you the citation. Yes, we could, but not from what I'm showing you. And the bottom line was, it was the message, the work message. Get a job, any job, sooner rather than later. You know, don't wait for a long time. Every office had a different way of operating and a different ethic and a different culture and so on and so forth. And MDRC had the good sense to collect survey data on how every one of those 59 offices worked. This is across 3 completely different studies over a period of a decade. So when we put all the data together, we actually had answers to the same survey questions about how these offices are run. This is another once-in-a-lifetime thing for me. And so we actually were able to do an analysis where we had really interesting data on these offices. And a number of things mattered, but the thing that dominated everything was the work message. Get a job, any job, sooner rather than later. And then work your way up. You know, don't wait. Don't just go to school hoping you'll find a job. Don't not go to school, but get a job. And the emphasis on that seemed to just have an amazingly strong relationship with whether the impact on earnings. All right, but that's not in this. This is a completely different thing. Impact variation. What do you tell a federal policymaker? Right.
Well, it's hard to imagine answering that question without, like, I mean, you could say, yes, this program works, but there's significant variation.
Okay.
And then they're going to say, well, why? So that's why I wanted to know the why question.
Okay. So you can report the variation. What's another way of reporting the variation? If you look at the histogram, or if you don't even look at the histogram, what if you say, well, you know, is this program harmful? To what extent is this program ever harmful? To what extent does being assigned to this program cause you to end up earning less than you otherwise would have earned, right? So, you know, do no harm. So one thing you might be interested in reporting is what does that bottom tail look like? What percentage of the sites, as best as you can tell, actually produced negative results? Yes? Well, you might want to get nuanced, but if you wanted to ask if you were using, yes, you might want to use a caterpillar plot. But you might want to summarize. That's an interesting point. But another way of doing it is just summarize what percentage of these. This is an estimate of a distribution. And you might step back and say, I have the mean of the distribution. I estimated that. I have the standard deviation of the distribution. I estimated that. I think the mean was $875 and standard deviation $742. If you assume that this distribution is approximately normal, this is another way to just come at it, because we can't know, okay? At least not given what I've told you, and not given what I think we know methodologically at this point in time. You can't know. But if it were if the distribution of 2 impacts were approximately negative, then in the population represented by this sample of 59, not in the sample of these 59, but in the population represented by these 59, what percentage are likely to generate negative results? And you could figure that out by just taking, you know, the mean plus or minus 2 times, you know, 1.96 times the standard deviation, and figure out what percentage of the sites in the population are likely to generate negative results. Okay, this gets to be a bit of art, sort of reporting the stuff. And then qualifying it maybe by going in and do you have any sites where you actually know for that site it was a negative impact, which is sitting behind your point. You may not know that even in large sites. Even the smallest sites, the largest sites might not have been large enough, but in this case maybe you would have. But what you're doing is you're relying on the whole distribution to give you some rough sense of what that distribution looks like, and therefore what the implications are for negative results, how often it could be negative. If you're running a local welfare office instead of a federal policymaker, you might want to say, what sort of risk am I exposing myself to and my organization to by implementing these kinds of programs? Then you really do care about the whole distribution. You might care about the negative tail in particular, but you might care about the whole distribution. And the more varied the impacts are across sites, the more risk you are taking on by implementing this, unless you know exactly what caused the variation. So obviously, if we could tell people what caused the variation, that's far more information for a local policymaker or a federal policymaker than just the variation. But quite frankly, we have not been reporting even the variation in the right way yet. When it's reported, as I said before, now I'm just repeating myself tenfold, usually it's a histogram or some kind of summary of the point estimates, which is, as I said, completely illusory unless the sites are even larger than these. So with that, yeah?
So, yeah, I mean, I think the usual, as far as I can see, the main findings from most of these huge multi-million-dollar multi-site trials, of which there have been apparently close to 200 funded, probably to the tune of like 1.5 billion or more, I don't know, huge number, by IES. The usual summary mainly is, here's the average, here's the p-value, 25. That's the main finding. You know, maybe some other stuff about different subgroups of people. Uh, but, you know, that's what you see under what worked somewhere.
Sometime for someone.
And I think most policymakers would sort of walk away thinking that's going to, what's going to happen to me if I do this to my site, or, you know, decision makers on site. So some deviation from that seems called for. One thing that occurred to me when you were talking was we should try to figure out how to formally test some hypotheses. Like, what's the null hypothesis? The null hypothesis that no effect is negative. You know, we can figure out how to do that, or maybe some more nuanced. Of course, the other question is, what about how big the impact can be? Can really do it.
Right. That's at the other end. Right. Okay. Why don't we stop? The break is, how long is the break? 15 minutes, so if we can start again about 9:45, I'll see you then. Is there a water fountain here? Oh, there we go. Thank you.
Because he knows more about
Thank you. No problem. Yeah, yeah, yeah. He reminded me.
Movies are made of that house.
He reminded me of a British government that recently collapsed because of that. Oh no, I don't want to go down that road. I don't want to go down that road. Let somebody ask me about it. But thank you. We know that's what I want to do for our paper too. I want to make darn sure that what's in there is what we think is what's in there. Can you guys hear me? I'm back on mic, right? Yeah, yeah. I'm resonating down here for some reason or another. All right. So I want to now address a question that was asked. I guess it was by Chris or when he was back there, or by somebody about how do you think about the statistical power or the statistical precision of this kind of an analysis for different kinds of designs. All right, and what we're going to do is we're going to talk about how come it's not up there. It's on here. I can see it. How come it's not projecting? Can we get somebody?
I can pretend like I know what I'm doing.
All right.
F5.
All right. You both got it. Thank you. Thank you. All right. So I want to talk about now the assessing statistical power or statistical precision. And in particular, I want to talk about how does the number of sites, call it capital J, and the size of the samples at the sites, lowercase n, how does that affect precision or power? What other factors influence precision? And how should this information be used to design trials if you're lucky enough to be in a position to actually design a trial? The designs that I'm going to talk about mostly multi-site individually randomized trials, which is what I was talking about previously in terms of the estimation model. Okay, I'm really probably not going to talk about multi-site cluster randomized trials because one, we're not going to have enough time, and two, it's a little bit more messy. The notation has a few more terms floating around, and three, it is my opinion, and I think it's shared at least by Mike, that the prospect for using cluster randomized multi-site trials to study cross-site impact variation because of its limited precision is probably not nearly as strong as it is for individually randomized trials. So we're going to focus on individually randomized trials. But in the paper, which is the basis for this, which is one of the references that you have access to, we talk about both. And my co-author here is Jessica Spybrook, who is a professor in the School of Education at Western Michigan, a former student of Steve's, and we've been working together with Steve for many, many years on related kind of things. So and that's the paper down here. All right. So what we're going to look at is precision for estimating three different parameters of a cross-site impact distribution. One, precision for estimating the grand mean, the mean of the site means. Two, the precision for estimating the cross-site standard deviation of impacts. And three, the precision for estimating the simplest possible site-level moderator effect, which is the difference of mean impacts between two categories of sites, subgroups of sites. Okay, that's what we're going to talk about. And that's what we're going to talk about. Obviously, we'd like to take it even further, but you got to start somewhere, and even that part is not as fully understood as it ought to be. Okay, so that's what we're going to talk about. Now, so first of all, you all know what a standardized effect size is, and we're going to talk about everything in effect sizes. The same conversation could be had in terms of impacts in their original units, dollars or points on a test, or percent passing a test, or percent failing a test, or percent graduating, whatever. But we're going to talk about something called a minimum detectable effect size and variance thereof. How many people are familiar with the concept of a minimum detectable effect size? Is there anybody that's not? Good. All right. So that's the way we're going to formulate it. In the kind of applied work in sort of the evaluation research world that I have lived in throughout my career, minimum detectable effects and effect sizes is really the coin of the realm when people are talking about powering a study. But of course, in other disciplines, which lots of you represent, people report out in terms of power. It's the same thing, formulated different ways, thought about different ways. But a minimum detectable effect size, for the kinds of audiences we work with, it seems like a metric that people can wrap their minds around. Then you can decide, is this minimum detectable effect size too big to be useful? Or is it small enough to be useful? And that's a whole other conversation about which we've done some writing, but that's not what we're talking about here today. But it's all about compared to what. And so we've done some empirical work in terms of compared to what. But that's not this. But that's where it goes in terms of minimum detectable effect size. Okay? Is it small enough to be useful? All right? Now, so then we're going to apply that concept to the mean impact, the cross-site mean impact, the cross-site standard deviation of impacts, and a cross-site category difference of mean impacts. Okay? Now, so just something that to remind you of what we're looking at. Here is a stylized cross-site distribution of impacts with a grand mean of beta, same notation as before, and a standard deviation of tau star. I changed this was on purpose. This was not a mistake. I changed we changed the standard deviation here because we're in effect sizes. It's a star because it's in standard deviation units, and so we're just keeping track. It's a minimum detectable effect size, not a minimum detectable effect. A minimum detectable effect would be in its original units. A minimum detectable effect size would be in standardized z-score units. That's all. So I just changed the notation here. That's still the cross-site standard deviation, but it's the cross-site standard deviation of effect size. Okay? And we're interested in estimating both of those things, and we're interested in knowing the precision of those things. So we're interested in knowing how the number of sites, capital J, and the size of the site samples, lowercase n, affects the precision of our estimates of this and our estimates of that for the first part of this talk. All right. So we're back to our model, our FERC model, fixed intercept random coefficient model for estimating a cross-site mean and a cross-site variance, and therefore standard deviation of impacts. So this is just repeating the model, hopefully in similar notation. All right, that's the model we talked about before. That's the basic model at the individual level, only now we've added individual level covariates. I said you could do that if you wanted in my talk last hour. So in this model, we have them in there. We'd say you could have a covariate or covariates. That's IJ. That's an individual level baseline characteristic, like a pretest or gender or something, eligible for free and reduced price line, those kinds of things. And so we just added that to the basic model we've been talking about before. But everything else that I said before follows with an additional twist that we're getting some additional precision out of that covariate. Okay, and we want to take that into account when we're powering our study. And a pretest, it has been my experience, and it's no news to anybody, but I've worked across lots of different domains over the years. In any domain you pick, any domain I've ever been working in, a pretest of one sort or another, a measure of the outcome previously is the best predictor of a measure of outcomes subsequently that you could ever lay your hands on. So, and having a good pretest could be like doubling or tripling or quadrupling the size of your sample sometimes in terms of the kind of power improvement you get. So that it's worth thinking about. Now, level 2, same model as before, fixed intercepts for each site, random variation in the impact across sites around the grand mean. We're now going to bring in some, so the random variation of impacts across sites is that error term there, and therefore that thing has the same, this has the same distribution as that. Well, this has the same variance as that, different mean. The mean 0, the error term is mean 0, and variance tau squared. Okay, that's just the same model. But now we're going to be thinking about precision, and so we're bringing in some other pieces of the model a little more explicitly than we did before. And this term here is the residual error variance. It's the residual error variance at the individual level. Sigma squared sub conditional on x, the covariates, and aj, the intercepts. How much variation do you have? And what that is, this term here, which is the term that's going to determine a lot of your precision, a lot of your power, so it's worth thinking about carefully. This is the variation in outcomes across individuals. For a moment, let's just talk about the control group within a site, for starters, controlling for the x or x's. So it's the residual within site control group variance across individuals. That's what this is. Okay, and if you think about it for a second, if you just had one site and you ran a regression like this for one site, and you're estimating Bj for that site, okay, its error variance would be a direct function of this. It would be sigma squared, that sigma squared, for that site, divided by, as it turns out, the sample size for that site, n, times t, one way of expressing it, times t bar times 1 minus t bar. But the point here is that this is what's going to determine the error variance, the Vj that I was talking about before, the error variance of this thing here, which is the square of its standard error. So this is what you care about in terms of individual level. And this, and this is a way of expressing the relationship between the overall control group variance of outcomes across all individuals from all sites, and getting from that to the within site control group variation condition on what site you're in and condition on your covariance. Okay? I'm not going to talk too much about this for the time being, but I just want to get you the basic idea. Because in this model here, you've got two explanatory variables, right? You've got site indicators. I mean, think of those intercepts as explanatory variables. You've got site indicators, right? And alpha j is actually could be thought of as a coefficient on a dummy variable for the site. You know, 1 if it's the site, that site j, and 0 if the person's not from that site. So that basically, those AJs are really representing a form of statistical control where you're going from the total variation in outcomes across all individuals from all sites to the within site variation across individuals. And what it turns out is that this thing here is what gets you from all variation across individuals and control group across sites to within group variation across sites. And then this takes this takes into account the fact that they're covariates, which is explaining the within site variation across individuals. So if you had pretest, okay, that pretest might have some r squared c within. It might have some explanatory power if you had 20 control group members and you had a pretest and you included that in your model. The residual variation controlling for the pretest might be much smaller than the original variation, and that r squared is a reflection of just how much smaller. So these two pieces are taking into account the explanatory power of your site indicators that goes from total variation to within site variation, and then the explanatory power within site of your covariates. That's a way to keep track of the two pieces that are at work there. And these are parameters whose values exist for certain kind of studies with certain kind of outcomes and certain kind of situations in literatures. You're going to have to guess at these things. Okay? And part of what we've been doing in other realms is trying to estimate these things, like in cluster random assignment, which I assume all of you are familiar with. You know, back a dozen or so years ago, there was hardly any information on. This is an interclass correlation. This is the interclass correlation. This rho sub c is the interclass correlation of control group outcomes within sites. Okay, so there's some information about that. If your sites are schools, and you're talking about across, and you're randomizing kids within schools, there is literature out there which tells you something about interclass correlations. And your outcomes are test scores, there's literature out there. Otherwise, you have to guess about these things. But I just want to give you an idea of what the parameters at play are. So this is an interclass, 1 minus an interclass correlation, and this is 1 minus an r square. And there are, you know, a lot of us have reported out values for those things for certain kind of clusters and certain kind of outcomes and certain kind of covariates. There is a literature on that to at least be suggested. All right, now, so it turns out that you can show that the minimum detectable effect size, and when I say minimum detectable effect size, we're talking about the grand mean now, minimum detectable effect size, okay, is the minimum detectable grand mean effect size. It can be expressed as this closed form equation here, okay? This thing here is a multiplier that takes, this thing here under the square root is your standard error. It's your estimate of the standard error of your grand mean impact estimate. Everything under the square root sign, that's your standard error. You're going to have to guess at that. You're going to have to guess at that, okay? it's a standard error for a standardized variable where the outcome is in z-scores. Remember, everything's in effect size here. So this is an expression for an outcome that's in z-scores. There's a different expression for an outcome in its original units. But this is the expression for the standard error. Let's start with that. Okay? The standard error for the grand mean is a function. It has two error components. One which is visible and the other which isn't in this form. Okay? This is tau square in effect size metric. Okay? How much cross-site impact variation do you have? This is essentially, this is not essentially, this is Vj. This is tau square plus Vj. Period. This is tau square plus Vj divided by the number of sites. For each site, we're assuming sites are all this, for a power calculation, you have to make simplifying assumptions. So you assume that all sites are of the same size and all sites have the same value of t-bar, the same percentage randomized to treatment and control, and you're going to guesstimate what what those averages probably are and so on and so forth. So all these power calculations are on a highly stylized situation, which is pretty much the only way you can kind of come at it. I mean, you have to make some simplifying assumptions. But basically, that thing there is Vj for a single site. And if all sites are same sample structure, that's Vj for every site, which is the simplifying assumption there, divided by the number of sites, which is simply a mean. It's an expression for taking the variance of individuals and turning it into the variance of mean, right? Variance of individual sites, that's the Vj, divided by number of sites, that's the variance of mean. So that should, having said that, that should feel familiar. But this variance for each site has two terms in it, which is different than how some of you might normally think about it. It has the error variance of the estimate for each site. So you have a given site, and you estimate it's Bj, and there's error in there. So you could overestimate it by a lot or a little, or underestimate it by a lot. Or so there's certain error variance there for a given site. But remember, this model that we're talking about, the population model, the theoretical model, is a model of sampling one way or another, either through convenience samples or probability samples. But somehow you're thinking in terms of, well, I've got a sample from some population of sites, regardless of how well I can explain that population of sites. And what I'm talking about is I'm trying to infer the parameters of the cross-site distribution for the population, not for the sample. That's how we're thinking about all of this. And so in your sample, you have a set of sites, but they're a sample of sites from some population. So you might have by chance gotten this sample of sites for your experiment, or you might have gotten that sample of sites, or you might have gotten this sample of sites. And depending upon which sample of sites you got, you could have gotten a different true average impact for this sample and that sample and that sample. You with me? Okay, by chance, any given study could have had a different set of sites with a different set of true impacts. So that thing there is the variance of those possibilities. Okay, divided by j, if you want to separate this into two pieces, divided by j, because everything's divided by j here. That, in a sense, is the result of the site sampling in terms of the piece of the standard error of the overall mean due to site sampling. Okay, ditto, or likewise, or by analogy, similar. This thing here is the part of the uncertainty in the grand mean estimate that's due not to the sites that you sampled, but to the individuals that you sample and the way you randomize them within site. That's your estimation error. Estimation error comes from randomizing. You could have randomized, in one case, a situation where the treatment group members have higher average counterfactual outcomes than the control group members, or vice versa, by a lot, by a little. Okay, so you've got within site sampling error, and you've got site sampling error in this model that we're dealing with. And these two components are part of the standard error of the grand mean estimate. Does that make sense? Questions, comments, thoughts? All right. This thing here is, if you know what minimum detectable effects are, then you sort of know what this term is, and I don't want to explain exactly where it comes from. But this is where you translate from standard errors to minimum detectable effects. And there's a nice little graphic way to describe what that M actually means, and it's in various things we've written over the years. And if you're interested, I can point you to something that describes that. But if J, the number of sites in this case, is above 25 or 20, thereabouts, probably even about 15. This number approaches the value of about 2.8 pretty rapidly. And what it's doing is when you're talking about a minimum detectable effect size, you have to define it very explicitly. And you have to define it in terms of what level of statistical significance are you using to test the hypothesis of no effect or no variation effect or no difference in effect. Those three parameters we're interested in, right? So what level of statistical significance? This is defined at the 0.05 level. You could have defined it differently, but it's sort of conventional as I've seen it, defined at 0.05 level, statistical significance 0.05. So this is the multiplier for statistical significance at 0.05 for a two-tailed test with a power level, an implicit power level of 80%. So that multiple, which takes the standard error, which is what it is, and turns it into a minimum detectable effect size, says if we're testing our hypothesis of zero mean impact at the 0.0 level with a two-tailed test, and we want 80% power, we want an effect that has 80% power, what's the smallest true mean effect that we have 80% power of finding at the 0.05 level? That's what it is. Does that make sense? All right. And that's an expression for it. And you could put that on a spread. Now, optimal design, which is a program that Steve and others, and I've been involved in it, and Jessica have been involved in it, does this automatically for you. I've always found it useful, for me at least, like to do things by hand the first time before I ever do it. And a spreadsheet is about as close to doing something by hand nowadays as you can get. And so I would urge you, in fact, there's part of an assignment for this little breakout session. You get on a spreadsheet and play with this thing and see what it says. Okay, but this is the expression. Now, what do you think is affecting your minimum detectable effect here? I mean, let's look at tau square. What is that telling you in that expression? What is tau square telling you? Can you put it in words? As tau square gets larger, and when tau square gets larger, what does that mean in terms of cross-site impact variation? Just in words. Cross-site impact variation is increasing. As cross-site impact variation increases, the standard error of our mean impact estimate, what? Increases. Now, why is that in words, intuitively? Why is that so, given what we've just said sits behind this process? You could have drawn a sample that had this mean true impact, or that mean impact, or that mean impact. Now, when tau square is small, it would be this mean impact, or that mean impact, or that mean impact. Tau square is large, it could be that one, this one, and that one. You see what I'm saying? So the more variability there is in the population of sites in terms of their mean impacts, their site mean impacts, okay, the more chance you have of estimating a grand mean impact that's too high or too low, okay, other things being equal, like that other component of the expression.
So Howard, I hate to obsess about the what works but do they make you put that tau squared in there when they tell you that you found a significant effect?
No, not to my knowledge. I mean, I don't.
I think then it really is the what works somewhere because, right, the tau squared says it adjusts for the fact that the impacts vary.
Right. The true impacts vary. The true impacts vary.
Unless they want to rename it.
Well, I don't know that because even if they vary, but you don't have a superpopulation model.
Right, right. And we don't want to go down that.
You don't want to go down that.
But yes, there are people who think differently about how to do these inferences in the first place and what population you should be inferring.
Not willing to let it go that easy. What works is a generalized statement. That's why I say, is it the what works clearinghouse or is it what worked somewhere clearinghouse? So the language matters.
Yeah.
The language says it's superpopulation. You're generalizing. What works?
I mean, I'm not disputing that, but there are, as we all know, there are people who would.
But I'm just trying to really get fussy about it.
Right. Well, that's what I was doing with impact estimates and impacts. I mean, the language matters a lot. Absolutely. All right. But so we are taking a population perspective because we think you're almost always generalizing beyond your sample of sites or your sample of individuals within sites, and that when you're trying to make a generalization, you want to take this piece of uncertainty directly into account, which is Steve's point. The Rutledge Clearinghouse, to my knowledge, and I don't follow them very closely, doesn't do that, or doesn't require you to do that. All right. The other piece is, again, for this site, you could have sites that all had the same impact. It's true impact. But for this site, you overestimated it. And for that site, you underestimated, and so on and so forth. So you would still have uncertainty in your estimate of the grand mean impact. You put those two pieces together because they're both at play. Okay? And that's what you want to look at when you're thinking about the precision of the grand mean impact estimate. They're both at play. Okay? And then when you ask the question, okay, how much does the number of sites matter with respect to the minimum detectable effect size? And how much does site sample size matter with respect to minimum detectable effect size? You got to look at both pieces. You got to look at both pieces. Now, before we move on to a table of findings from this result, look at that expression and tell me, in a proportional sense, if you were able to increase the size of each little n, if you were able to increase the size of the sample at each site by 50%, or instead, you'd keep little n the same, increase the number of sites by 50%. Okay? Which do you think would have the greater influence on your minimum detectable effect, reduce your minimum detectable effect, and why? Why? Yes, why?
Well, just algebraic.
Yeah, that's okay.
If you increase n, you're only decreasing the term that's added to tau squared.
Right. It only operates over.
Decrease j, you're actually increasing what you divide by, the entire expression.
Yes. It's that simple. It's that simple. So for estimating a grand mean, and for thinking about a minimum detectable effect size, which is defined with respect to a grand mean, the number of sites proportionally is more important than the size of the sites. Of course, if you can increase everything, that's not the way we're posing it. All right, so let's see, just make a little table of that. Oh, what did I do? Oh, one thing. When you're doing this sort of thing, when you want to talk about the site sample size, the value of n, and you might have a study, or you might be planning a study where the sites vary in sample size or something like that, in order to use these expressions, you want to take the harmonic mean value of n across sites that you anticipate, rather than the arithmetic mean. Okay, there are clear reasons for that. The harmonic mean can be much smaller than the arithmetic mean. So if you use the arithmetic mean, you might be fooling yourself in terms of thinking you had more precision than you actually would have. So for example, in the welfare to work study, okay, that we talked about, the arithmetic mean sample size, which you saw on a prior slide, right, was 1,176 individuals per site on average. You add up the total number of individuals, you divide by 59 sites, that's where that comes from, right? The harmonic mean is half that size. And it's the harmonic mean site sample size that you should be using in any power calculations or precision calculations that you do, because that's what matters. Okay, that's what needs to be in these simplifying expressions where you just have one value of n. It should be the harmonic mean value of n that you anticipate, okay? Likewise, for the Head Start, we had, that's where sample sizes range from 177 to over 4,000, just as a little context for you. And that's what made this darn thing so small, as it turns out. Okay, the more variability it is, the bigger the difference between the arithmetic mean and the harmonic mean, as it turns out. Think about that. That's actually, I found it really useful once I learned this, to think about why that happened and what that means. Okay, Head Start, where you got from 2 to 75 individuals per site. Okay, the arithmetic mean number of individuals per site was 19, and the harmonic mean was 13. It wasn't as different. The distribution, I mean, 2 to 75 is different, but those are the two tails. Those are the two extremes. So it's probably not well representing what that distribution really looks like. But you don't get as much difference. But again, this is smaller than this. And this is what matters for power. Okay? Now, so that said, let's take a look at a little table I made, the sort of table that I would urge you to make, and I think I put in an assignment for the next segment, where, okay, MDES for a cross-site mean effect size, individual randomization, that's the distinguished from cluster randomization. individuals per site, and this slide is in the paper, where you have number of sites, 5, 10, 20, 50, 100, 200, number of individuals per site. The note in the table tries to define the table. So we're saying we're talking about minimum detectable effects for a two-tailed significance test at the 0.05 level, where power is at 80%. You have a single level 1 baseline covariant. Remember, that's the X in your estimation model. It could be X's. That's the X. And call it a pretest. I'm saying that the R square of that pretest with respect to within site outcomes is about 0.4. And again, there's a whole literature on that. You know, if it's test scores on test scores or something else on something else, there's literatures out there to guesstimate these things. The intra-class correlation, I'm saying if you were individually random, if you're randomizing individuals in schools, and inter-class correlation across schools might be in the realm of 0.1 to 0.2 or thereabouts, depending upon whether it's elementary schools, middle schools, high schools, and depending upon the outcome, blah, 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 blah. If it's test scores, it's probably around 0.15. If it's just drug, sex, and alcohol, it's probably about 0.02. Think about that. That has important implications for behavior. And think about why that's so. But anyway, presume it's test scores for 0.15. These are parameters that you had, two t-bars 0.5. What does that mean in terms of the treatment and control group? Size? They're the same. T-bars 0.5 means 50-50 treatment and control. People see that? Constant n within sites. And now one more assumption that I had to make to fill out this table is how much cross-site heterogeneity and impacts do I think there really will be? Again, why? Because you might get a draw of sites over here, sites over here, sites over there. You want to know how different might those draws be just in terms of true mean impacts for your samples. So you have to assume that too. And if you assume those things, and then you fill in, this is J, right? And this is N, different combinations of J and N, you see a bunch of numbers here. And these are in effect size. So for example, if you had, and I've shaded this diagonal here, so let's go to this diagonal. If you had 5 sites with 200 individuals per site, the minimum detectable effect size, and I assumed all these things here, the minimum detectable effect size would be 0.30 standard deviation, test score standard deviation. You with me? Okay. If instead you had 10 sites and 100 individuals per site, the minimum, same total number of individuals. How many individuals are we talking about here? 1,000. Now we move here. Hold constant, 1,000 individuals, but they're allocated across sites differently. What do you get? Minimum detectable effect of 0.21. Same number of individuals total. 0.17. More sites. More sites. More sites, more smaller sites, more smaller sites, more smaller sites given total number. The minimum detectable effect gets smaller, 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 smaller. You see here, obviously not a surprise, what was sitting in the equation, which was what generated these numbers, but you know, it also gives you, once you actually look at the numbers, some sense of importance, magnitude of the trade-off between site size, site sample size, and number of sites. For a situation that looks like this, and in particular a situation that looks like that. Yes? Yes, because t-bar is 0.5, so yes. And the way we're using n is we're not doing n sub t or n sub c, we're doing n and then times t-bar. Okay, that's the number of treatment group members, and n times 1 minus t-bar is the number of control group members. So n is the total number of treatment control group members per site.
Howard, you just spent a lot of money to get that extra last 100 sites.
Right, it's something like diminishing marginal returns to sites. Yes, yes. Mike, you were going to say something. Oh, I thought you were. Other thoughts? And you can sort of see this throughout the table. Now, then, the severity of the story that happens along the diagonal. I mean, the diagonal is the easiest place to track this, the particular story we're looking at right now. That would change as tau star changes. Why? And how? Let me make it easier. Why and how? Yes, Josh.
So the greater tau star is, the more important sites are going to be to decreasing your minimal detectable
Effect
size,
size.
right?
Right,
Now tau is a bigger part of what you're dividing by.
right. What if tau's 0? What if all sites have the same mean effect size? Then what's the trade-off between number of sites and size of site sample? They're interchangeable because they're both operating exactly the way. They're both operating in the denominator of this term, period. If you increase j by 50% and hold n constant, it's the same as if you increased n by 50% and held j constant. So what determines the severity of the trade-off between number of sites and size of sites is tau squared. So if you think there's a lot of heterogeneity out there, then sites really matter. Number of sites really matter. If you think there's not very much heterogeneity out there, maybe you can have bigger sites, and so on, and fewer bigger sites. Because the costs of recruiting sites is non-trivial. And the care and feeding of sites. Not only you've got to recruit them, but you got to keep them in a study, and you got to work with them and train them so that the study can actually be run in a reasonable way, and so on and so forth. So that's big bucks. Okay, so if you the marginal cost of another site has got to be vastly, vastly larger than the marginal cost of another individual in a site, and there's not good data, and if it were, it would be all proprietary. I assure you about those trade-offs. If I had it, I wouldn't give it to anybody. I'll tell you that. I don't have it. That's for sure. I don't have it. But anyway, but that's what you're doing. You're doing a cost-effectiveness analysis with respect to minimum detectable effect size, and either formally or informally. And it's not just a financial cost. I mean, recruiting sites and keeping sites on board and trying to figure out how to make that happen, that's an art form. Okay, and that's a very difficult task. And so the fewer sites you have to work with, the easier that task becomes.
Do you have simulations? So when you're trying to save costs, one thing you do is maybe the recruiting sites is expensive, maybe the treatment itself is expensive, so you can reduce the number of treatments to be.
Yes, you change T-bar. You change T-bar, yes.
Do you have information that shows that trade-off?
That's easy. I learned that about 40 years ago in real time, which is exactly what I was telling you. There's something called the National JTPA study, which precedes all of these experiments that we've been talking about recently. And it actually was a precedent-setting thing that it moved experiments into more of the applied policy work, okay? And that's how I got connected to MDRC. I ended up being co-PI of that with Judy Garone, who was president of MDRC, and a guy by the name of Larry Orr, who was at Apt Associates at the time. And we were trying to recruit sites. I mean, not me. I don't go to sites. They wouldn't dare let that happen. So we're trying to recruit sites in real time. And the JTPA study was being done under a national randomized experiment. This was backstory. There was supposed to be a big study, a non-experimental study, a longitudinal non-experimental study. It got canceled because there was this panel that said, we've already done this with the prior program, and it didn't work. And I don't know if you know Becca Maynard and Bob Lalonde. There's this whole literature about experimental and non-experimental findings, blah, 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 blah. Well, that nascent literature caused the design of the study to change in real time, whereas the contract had already been let. The contractor was ready to go, and they said, no, we're not going to do this quasi-experimental study. We're going to do a randomized experiment. We're going to put it out for bids. Okay, so we put together a team and so on and so forth. But anyway, we're now doing the study, and the JTPA, we didn't have much leverage on the sites. There was not really a big incentive for sites to participate. Didn't affect any of their money, didn't affect hardly anything. It was more goodwill, for the better of the community sort of thing. And that only goes so far in these environments. And so somebody came to me and said, well, what if we could recruit fewer control group members at each site? What would that do? And I didn't know this at the time. But I read an article by a guy whose name I'm blanking on, and I realized that the VJ is equal to sigma squared over n times T bar times 1 minus T bar. T bar times 1 minus T bar, okay, is largest, which means the variance is smallest, when T bar is equal to what? 0.5. Go ahead.
But I guess I mean in this context, because of the tau squared, now it seems to me that the sites is much more important than you could shift that ratio, but it's going to be swamped by the tau squared.
Right, that's where I'm going. Even if it weren't, even if VJ mattered, this is really worth knowing, because even if VJ mattered, even if tau squared were 0, okay, a t-bar of 0.5 is 0.5. T-bar times 1 minus t-bar is 0.25, right? What if it's 0.6 and 0.4? 0.24. What if it's 0.7 and 0.3? 0.21. How different is 0.21 from 0.25? And now you've already gone from a 50-50 treatment and control to a 70-30 treatment and control. You have barely changed your precision, okay? And we said, okay, let's do that. All of a sudden, I mean, they didn't come flocking. The sites didn't come flocking. All of a sudden, we were able to recruit sites for that study, and we would have never been able to recruit sites otherwise. So that's just a more general lesson. The T-bar doesn't really matter much until you get in the extremes. All right?
The other part of that, so that's about treatment allocation
Within site.
two groups. And as far as deciding on the optimal N, I'm not sure if that was where you were going. Kind of, what's the optimal sample size per site? Is another.
I guess what I thought, if I fall into the bad question variety, is that one way you save money is by treating less students because you can shift a little bit and not cost yourself so much.
Right.
But is this telling us that because of the tau square that maybe we were thinking about clearly enough before, that by shifting the number of students within the site, it's actually not changing our MDS very much because the tau square, because natural variability is
Yeah, I think
kind of
there's two
swapping that
issues.
out a
One
little bit.
is, I think the focus right here was on T-bar. Should, what does it matter if it's 0.5, 0.4, 0.3, whatever? What's related, of course, is how much does the N itself matter? And that depends on the tau squared and the sigma. Well, the sigma squared is being held at constant 1, but
Right,
it really
right.
depends on those two things.
Right.
And the cost ratio. So at least in the cluster randomized trial part of the optimal design, you can plug in numbers for costs and variances and get the optimal N. That goes back to William Cochrane, 1957, optimizing on the cluster sample, how many clusters, how
Right.
many people per cluster. So these are some things that you can easily obtain for any design. Do a little bit of work, is to get the optimal N. There's some really cool stuff. You asked about cost. You can get the optimal P under some cost.
Right.
Under the relative cost.
Right. The treatment, that's why I responded the way I did. You came in with a story about treatment costs more than control, therefore T-bar matters, and that's what I was building on. And I'm saying that T-bar usually doesn't matter much regardless of the value of T squared, but it certainly doesn't matter much as the tau square gets larger.
I wanted to ask you one thing. So were you saying that the site people really wanted more people in the experimental group?
They didn't want to turn away people.
Right, exactly. So they wanted a smaller control group.
They wanted small, that's what I said. Was it what I said?
So in some sense, there was a funny kind of cost on having a big control group sort of increase the cost in a certain sense because the recruiting is much harder. So
Recruiting is harder.
yeah.
Well, I think,
Optimize your T-bar, you can optimize your N, and then you just buy as many sites as you have until you just spend money until your money runs out buying sites.
right.
That's kind of the way it works.
And buying sites, there's money and then there's a lot of other stuff. Money is the small part in a lot of time.
Well, but you need a cost estimate,
Right.
right? I mean, if you're going to spend enough, I mean, really, well, I don't mean to be one of these coming from the University of Chicago, everything has a price, right? I mean,
Well,
if you buy your site, you don't get enough money.
yeah.
You can give people money, you can participate.
right. But you can oversell that too.
And you can hire great people who are really good at recruiting. I mean, you can do a lot of things.
Well, that's what really matters.
So you got to come up, but I'm just saying to really optimize it, you have to have some rough estimate of C2, the cost for each sampling each site.
Right.
C1, once you're in a site, how much does it cost to recruit another and assess another person? Think about Head Start, where you've got to actually sit down in a room with each kid and assess each child. So the C1 is actually pretty high, which maybe that's part of the reason that they didn't have such big, I don't know if they didn't have such big samples per site. Because, how much did you get out of it, and yet it
That
costs.
right. That might have been a recruiting a limitation too, but it could have been a cost limitation.
But you know, you kind of try to figure, and if you just get some rough estimates of these things, you can avoid some gross errors, even if the estimates aren't totally right, and get a design that's actually going to be reasonably cost efficient.
Right, and these are guesses. And the best you can do are educated guesses. This is just a framework for what parameters do you need to guess about, and what are the implications of the variation in the values of those parameters. Michael.
Plug educated guesses into this framework, you're likely to come up with something a lot more rational than if you didn't understand all these things.
Absolutely, absolutely.
Just for the training for Jay, so in addition to managing cost, observer, this becomes an issue. The more sites you have, also fidelity can come down with it. Some observer considerations of, it just seems you're like, the more J the better. But I can imagine there might be use for the walls.
Absolutely. You have to manage those sites. You have to be able to implement the intervention in those sites. So you have to understand your capacity for doing those things. Absolutely. So that's part of the, quote, cost effectiveness set of trade-offs. It's many, many factors. But this at least can tell you what kind of precision you're trading off as you go for more sites and have to assume everything that goes along with that. Or you go for larger sites and you have to accommodate everything that goes along with that. Yes, absolutely. Okay? Now, so we're going to now move to, don't worry about that. When am I done? Am I done at noon? What? Really? Oh, shit. All right, no, I can do this. All right, so, sorry. It's a good thing Michael tracked me out with my mic on when I was standing out there. All right, so now we're going to do a similar kind of thing for the minimum detectable effect size standard deviation. I hate that acronym, but we haven't come up with anything better or that I hate less. But it's the minimum detectable effect size standard deviation. So there's a long appendix in the paper that kind of derives this. And we'll just go through it very, very quickly because I want to get to the next topic. You can see what now should be your old friend, the interclass correlation, the site level interclass correlation, the within site variance explained, n times t bar times 1 minus t bar, and then this stuff. Do you see J anywhere? You see n, and so as n goes up, this thing goes down, with the square root of n. You with me? Because n is sitting under the square root of n. You with me? But do you see J anywhere? Yeah, those are F statistics, and I don't want to say the words to try to describe what they are. They're in the paper, but those are F statistics under the null hypothesis and under the alternative hypothesis. And as J gets bigger, okay, that ratio moves toward 1. As the number of sites gets bigger, that ratio moves toward 1. Okay, so J's in there. You just can't see it as easily. Okay, so the only way to do it, well, not the only way, the way I then try to understand that is to create a table from that expression, again, where, again, we've got the same assumptions. The minimum detectable effect size standard deviation is defined the same way the minimum detectable effect size was defined in terms of significance at 0.05 for the variance, then therefore the standard deviation, power of 80% for the variance, and therefore the standard deviation, a single baseline covariate as before, the same interclass correlation, the same within site R square, and the same t bar, blah, blah, blah. And now, then, let's look at the results of the actual values of the minimum detectable cross-site standard deviations, talk about what they mean, and the trade-off between increasing number of sites and increasing the size of the sites. You with me? So first of all, what does this say? Well, let's stay on the diagonal. Okay, the same diagonal as before. Okay, we got 5 sites with 200 individuals per site, total individuals per site, randomized half the treatment, half the control, right? So the minimum detectable effect size standard deviation is 0.22. Okay, 0.22. That standard deviation is 0.22 standard deviations. It gets a little complicated to describe that because an effect size, the metric of effect size, is a standard deviation. So this is this is a standard deviation of a metric that's measured in standard deviations. Okay, so anyway, it's 0.22 standard deviations. It's called test score standard deviation. The cross-site impact standard deviation is 0.22 test score standard deviation, individual level test score standard deviation. Okay, if we go to 10 sites with 100 each, it goes to 0.21. if, I don't know why that happened. Well, it's just bouncing around, probably rounding, bouncing around. 0.22, now it's starting to go up. Now it's starting to go up. Now it's up. So we get to 200 sites with 5 each, and we have a minimum detectable effect size standard deviation almost twice the size of 5 sites with 200 each. That's the trade-off between N and J that's sitting inside that expression I gave you, where the J is sitting inside of the ratio of the F statistics, N is sitting right in the numerator of the expression. And that's the trade-off given all of this. Given these well, you're not assuming tau square anymore because now you're trying to estimate what's the minimum detectable value of tau. You with me? So you're not assuming a value of tau. You're trying to figure out what's the minimum detectable value of tau. All right? Now, I want to move on to do one thing, then I'll stop. I have 5 minutes, right?
Just one thing, notice that once you get above a certain number of sites, for a certain number of people per site, the only thing that matters is NJ.
But it's the number of people per site that matters more in here than the number of sites. Okay? Now, one thing that, frankly, I didn't realize until recently, I want to talk to you a little bit about minimum detectable effect size difference between 2 subgroups of sites. You with me? Okay, which is the simplest. It's a binary site level moderator coefficient. Okay, so I'll do it quick. So now what you're talking about is you imagine you have 2 categories of sites. Maybe it's rural, maybe it's urban. Okay, so you have 2 populations or 2 subpopulations of sites. And maybe we're specifying a model where there's a mean and a standard deviation for one subpopulation and a mean and standard deviation of another subpopulation. And this model, now that I'm thinking about it, assumes that the standard deviation of impacts across sites is the same, but the means might be different. Okay, that's what this model assumes. Okay, that's the simplest possible way to do this. Okay, what we want to do is we're estimating a beta 1 for one subpopulation and a beta 2 for the other population, and what we're interested in is the difference between those 2. How different is the average impact for those 2 subpopulations of sites, right? And what we want to know is what's the precision of our estimate of that, all right? Now, so our impact estimation model is just what we've done here is we've got the same level 1 model, the same individual level model as before. We've got Y as a function of whether you're in a treatment and control group and your baseline characteristic. Same as before with same assumptions, everything else. But now the level 2 model changes. Okay, we still got our fixed site intercepts, but now we're saying, look, the model of the average site impact says that what we got is Bj is a function of some average Bj for one group of sites plus delta, which is a coefficient. It's not delta W, I realize. Delta is a coefficient, which is difference, and that's what we're trying to estimate, times W, which is 1 for urban and 0 for rural or vice versa. You with me? And then a random error term. So, and this is a conditional random error term, which is the amount of variation that is within subgroups of sites. The amount of variation in true impacts that's within subgroups of sites. So if you go back up, give me maybe a couple, 2, 3 extra minutes. I want to finish this. So what you're saying is that, there's so much total variation across sites, which is a composite of all of that. But then there's a certain amount of variation within this subcategory, a certain amount of variation within that category, and part of the overall variation is due to the difference between the means of those 2 categories, right? All right. Now, so this thing here has got a basically its variance is tau square star conditional on W. It's the within site subgroup variance of true mean site impacts, right? And in a sense, not in a sense, and it is equal to 1 minus the level 2 R square, the R square of W, the R square at level 2 of your subgroup indicator. So it's 1 minus that R square times the unconditional tau square. You see what I'm saying? When you put this predictor in, it reduces the variance, the unexplained variance. It explains some of it. And this is just formalizing that relationship. That's a different R square. It's R squared for delta. It's actually R squared for W. But you know what I mean. All right. Now, so there's a twist to this, though. Because now there's 2 things that are different about this parameter than other parameters that I've talked about so far. One is that it's possible that for any given sample size, there is no And for any given definition of a minimum detectable effect size different, like defined at power at significance of 0.05 for a two-tailed test, power at 0.8 or 80%. It may be the case that there literally is no minimum detectable effect defined that way for certain sample designs. That it's impossible to get 80% power, no matter how big. For certain differences, not no matter how big, but it's impossible. It's impossible. So it turns out that there's not a closed form expression that you can just use here. And there's another twist to it. Let me see if I can explain. This is a little hard to explain. I don't think I've ever tried to explain this to other than my colleagues. Here is the standard error, an expression for the standard error of delta hat. Delta hat is the estimated site subgroup difference of mean impacts. You with me? This is an expression for that standard error. All right? Now, then, under certain conditions, it's possible that that standard error is so big because the site's so small and there are so few of them that there is no difference that you could detect at 80% power at the significance level 0.05. So that's one thing. The other thing is that the standard error itself is a function of the r squared, I call it r squared delta in one place and r squared w in the other place. It's the same thing. It's the actual explanatory power of delta. The standard error, for good reason, is a function of the r square of w. Okay, r squared of w is literally a simple function of the difference of mean impacts. So this gets circular, that you can't calculate a standard error without knowing r squared w, which means without knowing the difference, the true difference of impacts. It gets circular. Okay? I'm not explaining this well, but I'm pretty darn confident this is right. And so what that implies is a bit of a dance in trying to get a minimum detectable effect size difference of this sort. One is, and this tries to lay out, and I don't want to go through this formulas with no time, but there's some steps. One is you can determine the maximum difference in mean impacts for the two sites possible, given tau square star. If tau square star is equal to 0, what's the maximum difference in means for the two groups of sites? 0. There's no difference. All sites have the same impact. What does it mean to have tau square equal to 0? All sites have the same impact. Okay? So under that condition, there's no difference, period. 0 difference. Okay? If there's 0 difference, okay, so that's one thing. I'm going to try to do this right. So what you do is you take the maximum difference, and this is an expression where it would have r square up here, or 1 minus r square, I forget which way. And when and in the extreme, r square is equal to 1, the maximum difference you could have is when r square is equal to 1. What does that mean? That r square. That means all of the variation, okay, is between the two groups of sites. Between. That means those two curves collapse into 2 points, 2 spikes. Okay? Okay? You with me? Now, then, so that's the maximum. The maximum difference you could have is when r squared is equal to 1. So this then simplifies to this thing here. So you can actually derive what's the maximum difference you could possibly have by there's an expression in the paper which then simplifies to this when r squared is equal to 1, that r square. And you're assuming a tau square. Pi is the proportion of sites in one subgroup. 1 minus pi is the proportion of sites in the other subgroup. That's an expression. Okay? I'm not trying to teach you this. I just want to point you this so if you read the paper, you can sit and think about it for a while. Okay. So you take the maximum delta there could possibly be and calculate power for it. And here's an expression for power, and I don't want to describe it. But you do that. Okay? You calculate the power for that, given this expression for the standard error, et cetera, which is in there. And r squared is equal to 1. And you calculate the power for that. If that power is less than 80%, you stop. Because you can't get to 80%. the maximum difference gives you power less than 80%, you stop. If that power is greater than 80%, I mean, the way we're doing it and the way Jessica programmed a little thing in R, which she could make the code available to people, but you got to really understand what the ideas here are. If that's over 80%, you can then try a smaller delta. Work it through, figure out what the R square implied by that delta is. Figure out what the standard error implied by that R squared is. Work it through again. Figure out what the power of that is. And keep going down until you get to a delta, which implies an R square, which gives you 80% power. So that's how we're doing it and recommending it be done. And that's pretty new. I haven't even talked to Steve about that. I've talked to Mike about that, but not to Steve about that. But it's a real twist. And why is it, among other reasons, why is it a twist? Because the parameter, the standard error of the parameter, oh darn, yes. Okay, here's why. The reason that is so is because the standard error of the parameter you're trying to estimate is a function of the true value of the parameter. Because that R square is a function of the true delta. You may not see this, but I'm telling you this, and I'm pretty sure this statement is right. That R square reflects delta, and you're saying the standard error of your estimate is a function of the delta you're trying to estimate, and that gets circular. It's like a proportion. You know, it's like a proportion for good reason, because it's a binary variable, and that proportion is working on these values in the way that a proportion works. The variance of a proportion is equal to the value of the proportion. If you think about it, right? The variance, just simple proportion. The variance of a proportion is equal to the value of the proportion. It's p times 1 minus p. That's the variance, okay, implied by the proportion. And so a similar phenomenon is going on here for the exact same reason, because it's binary. And you have to do a little dance to get at this minimum detectable effect size difference. Now, that was a whole lot at the very end of my talk, for which I don't apologize, because I wanted to at least put it in front of you, so you might be curious enough to read about it.
Sorry, just like one small thing. In the expression for standard error down there, is R squared W supposed to be 1 if you're assuming the maximum delta?
Yes. And what happens? This term falls out, because you've explained all of that. And there's nothing inside of those two subgroups, no variation inside of those two subgroups.